It begins, as it so often does, with an image, a faint smudge against the black, captured by a network of telescopes, processed by automated software, and shared across the digital nervous system of humanity. But this smudge is different. It is Interstellar Comet 3I Atlas, and it is behaving strangely. By early 2025, the images circulating online are electric. They show the comet not as a gentle, fuzzy pearl, but as an object of intense, almost unnatural brightness. Public forums ignite. The object seems too bright for its distance, its coma, the gas cloud surrounding the nucleus, too expansive. Some images hint at a vibrant, unrealistic green, others at complex structures in the tail that defy simple explanation. The phenomenon goes viral, fueled by a potent mix of genuine awe and suspicion. The question is immediately asked, why does this visitor from another star look like this? In the scientific community, the reaction is one of cautious, intense scrutiny. We know this is 3I Atlas, the third confirmed interstellar object, detected on a hyperbolic trajectory that will never return. We know its orbit brings it close to Mars in October 2025, followed by a close pass of the Sun. We also know that the images causing the stir are processed. They are not raw data. They are the result of stacking multiple exposures, aligning pixels, and stretching contrast to reveal faint details. This introduces the first and most critical variable, the human hand. The anomalous brightness could be an artifact. Different software, different processing techniques, and different choices by the astrophotographer can dramatically alter a comet's appearance. A simple adjustment to the curves in an image editor can make a faint object appear to blaze. Furthermore, the striking green color, while evocative, is often enhanced. It points to the presence of dicarbon, which glows green when excited by solar radiation, a known phenomenon called the swan bands. But how much green is real, and how much is saturation bias? This is where media hygiene becomes essential. The discourse quickly splits. Is the scientific community silent on the anomaly? Or are they simply busy validating the data? There is a profound difference between a coordinated conspiracy and the institutional delays required for proper calibration and peer review. Before we can ask what the comet is doing, we must first rigorously prove what we are seeing. If the brightness anomaly is purely a processing artifact, then different observatories using standardized calibration methods should produce conflicting results. One team's blazing comet will be another's normal comet. Furthermore, if the anomaly is caused by Earth's own turbulent atmosphere, the seeing, then observations from space-based assets like the Hubble Space Telescope or JWST should show a different, cleaner picture. The viral image, therefore, is not an answer. It is the formulation of the question. Is a 3I Atlas truly undergoing an extraordinary outburst, or are we simply seeing a reflection of our own technology, our own atmosphere, and our own desire to witness the spectacular? The noise must be filtered from the signal. Before we chase interstellar ghosts, we must account for the distortion field generated by our own planet. The single greatest obstacle between us and any comet is the 100-kilometer thick shell of gas we breathe. All ground-based imagery, especially from amateur telescopes that generated the initial excitement, is subject to atmospheric seeing. The light from 3I Atlas travels unimpeded for trillions of kilometers, only to be bent, scattered, and blurred in the last milliseconds of its journey by pockets of turbulent air. This is what makes stars twinkle. For a faint, extended object like a comet, it's a disaster. It smears fine detail and can unpredictably spread the comet's light, making it appear larger and puffier than it truly is. Professional observatories fight this with adaptive optics, using lasers to create artificial guide stars and deformable mirrors that change shape hundreds of times a second to cancel out the atmospheric wobble. But even this is imperfect. The most reliable data must come from above the air. This is the first critical cross-check. If the viral brightness is merely an artifact of bad seeing, then simultaneous observations by the Hubble Space Telescope, or JWST, will not show the same dramatic brightening. They will reveal a sharper, more contained object. When the first calibrated space-based images are released, they confirm part of the suspicion. The comet is not as explosively bright as the most extreme viral images suggested. The edges are sharper, the core more defined. But the digital noise is a separate problem. The vibrant colors and high contrast in amateur photos are the result of stacking, combining hundreds of short exposures to build up a signal, and stretching, manipulating the brightness histogram. This is an art form, but it is not science. It is designed to produce a beautiful image, not a photometrically accurate one. An operator can easily, and often unintentionally, introduce a brightness spike that isn't real, or oversaturate the green C2 swan bands until they look like a special effect. If the anomaly is purely digital processing, then the raw, uncalibrated FITS files, the scientific standard data format, from these same telescopes will not contain the spike. When scientists analyze this raw data, they find the truth is in the middle. The processing did exaggerate the phenomenon, but when the artifacts are stripped away, the signal from 3I Atlas is still remarkably strong. The atmospheric and digital noise has been accounted for, but a core mystery remains. The comet is genuinely, unusually active. The why is not on Earth. It's inside the comet itself. With the terrestrial and digital static filtered out, we can finally listen to the comet itself. What is its baseline? What is its engine? We are observing this object as it makes its closest approach to our sun, a critical period peaking in late October 2025. This is its moment of maximum heating, and its engine is in overdrive. A comet's engine is sublimation, sunlight striking the nucleus and turning solid ices directly into gas. This gas, the coma, expands, and it's what we see. But the type of ice matters. Spectrometers on JWST and Hubble are dissecting the light from this coma. They find the chemical fingerprint is overwhelmingly dominated by carbon dioxide. $2. This is the key. Most comets from our own Oort cloud are water-dominated engines. They only become truly active inside the orbit of Mars. Our Atlas, born around another star, is a CO2 machine. This more volatile ice means it has been actively venting, much farther out in the cold. The early observations of OH raid hydroxyl, a fragment of H2O3, were present, but CO2 is clearly the primary driver. This gas doesn't vent cleanly, it drags dust off the nucleus. This dust reflects sunlight, accounting for a huge fraction of the comet's visible brightness. The gas itself glows via fluorescence. We see the spectral lines for CN-D, cyanogen. We see the C2-D-carbon, swan bands, confirming the genuine, if exaggerated, source of the green glow. This dust can also create optical illusions. As Earth passes through the comet's orbital plane, observers note a sharp anti-tail, a spike pointing toward the sun. This isn't gas-defying physics, it's a trick of perspective, a fan of larger, slower-moving dust particles left behind in the comet's orbit, which we are seeing edge on. But the gas is powerful. When these CO2 jets erupt from the sunlit side of the nucleus, they act like miniature rocket thrusters. We can measure this. If the comet's orbital path deviates even slightly from the trajectory dictated purely by the sun's gravity, it reveals non-gravitational acceleration. This subtle push is a direct physical measurement of how much material the comet is venting. It's a way to quantify the engine's power, separate from its brightness. Then, spectroscopy returns an even stranger signal. Observers report detecting metallic lines, specifically nickel, Ni, glowing in the coma. This is expected only very close to the sun, where temperatures can vaporize dust. But the anomaly is the reported absence of corresponding iron Fe lines. In our solar system, these two metals are almost always found together. Is this a truly alien composition, or a gap in our understanding of how these metals behave in a CO2-rich environment? This, then, is our baseline, a powerful CO2-driven engine, potentially rich in nickel, and throwing off a significant dust screen. This is the true comet. Now, what happens when this engine flies through a storm? The comet's CO2 engine provides its baseline brightness, but this comet is not traveling through a vacuum. It is flying through an active, hostile environment. The sun is not just a lamp, it is a cannon. It constantly fires a stream of charged particles, protons and electrons, into space at over 1,000,000 kilometers per hour. This is the solar wind. Facts and dates. Crucially, 3I or Atlas is arriving during the peak of solar cycle 25, a period of maximum solar activity predicted for 2024-2025. The sun is angry, covered in sunspots that erupt in solar flares, and, more importantly, coronal mass ejections, CMEs, billion-ton clouds of magnetized plasma. This is the space weather that the comet must endure, and it provides a powerful external X factor that can modulate the comet's appearance. This interaction is visible. As solar ultraviolet light ionizes the neutral gas, like CO2 in the coma, the solar wind's entrained magnetic field grabs these new ions, like it sweeps them away at high speed, forming a long, straight, narrow tail that glows, often blue. This is the plasma tail, distinct from the curved, dusty, sun-reflecting tail. This plasma tail is a solar windsock. It shows us exactly what the solar wind is doing. When a CME, a solar storm, washes over the comet, two things can happen. First, the CME's dense, tangled magnetic field can compress the entire coma, squeezing the gas and dust. This compression can cause a sudden flare in brightness, making the comet appear much more active than its nucleus engine truly is. Second, the conflicting magnetic fields can cause a disconnection event, where the comet's entire plasma tail is severed and drifts away, only for a new one to begin growing. This gives us a powerful, falsifiable hypothesis. If the viral brightness spike was not an artifact, part 2, and not a sustained nuclear outburst, part 3, it may have been a transient event caused by solar activity. We can test this. We must correlate the timeline. We check the data from solar observatories like SOHO, Stereo, and Solar Orbiter. Did they detect a CME or a high-speed solar wind stream that was aimed at 3I Atlas with the correct travel time to match the observed ground-based brightening? If yes, we have a likely culprit. Furthermore, the spectrum of the flare should be different. A nuclear outburst would increase all gas production, CO with $2, C $2, etc., relatively equally. A solar wind compression event would preferentially brighten the ionized gas already interacting with the wind, like the blue glowing keopolars. The viral image's brightness, therefore, might be a snapshot of a solar storm hitting an alien object. We have a suspect, the sun; we have a victim, the comet; but we have a contaminated crime scene. Observing from Earth, or even Earth's orbit, means we are inside the storm. We are too close to the sun, bathed in the same solar wind that is battering the comet. We cannot definitively separate the comet's own light, its engine, from the light induced by solar weather. We need a second opinion from a clean room, a vantage point far from Earth but close to the comet. We need Mars. By incredible orbital luck, Comet 3IO Atlas makes a close flyby of Mars on October 3, 2025. This is not just a photo op, it is a critical scientific opportunity. An entire fleet of advanced robotic spacecraft is already there. We have ESA's ExoMars Trace Gas Orbiter, TGO, and Mars Express. We have NASA's MRO, MAVEN, and the Perseverance rover on the ground. This fleet, designed to study the red planet, becomes our filter. MAVEN, built to study how the solar wind strips Mars's atmosphere, can perform an in situ measurement, potentially flying through the outer halo of the comet's coma. It can directly measure the solar wind particles at Mars's location and simultaneously sample the comet's own gas, separating the cause from the effect in real time. On MRO, the high-rise camera, a high-resolution telescope, can be pointed away from Mars to image the comet. It won't see a pretty picture, but it might resolve the nucleus from the dust jets, providing a clean measure of its core activity. TGO's spectrometers can stare at the comet, providing an independent, calibrated measurement of its CO2, HH2O, and O. composition, free from Earth's atmospheric blurring. This setup allows us to disentangle the variables. We get a stereoscopic view. If the anti-tail is an optical illusion, a trick of perspective, the Mars fleet will see it from a completely different angle, and it should vanish, resolving into a simple dust fan. This would confirm its nature. Most importantly, when a solar storm, a CME, erupts, SOHO, near Earth, will see it. Hours or days later, MAVEN at Mars will see the exact same storm arrive. By correlating these two data sets with the comet's brightness as seen from both planets, we can finally prove it. We can watch the CME hit the comet and see if MRO, TGO record a brightness flare at the exact predicted moment. This removes all ambiguity. This window is brief and vital. Shortly after the flyby, around October the 21st, 2025, Mars and the comet will move into solar superior conjunction. This means the sun will be directly between us and them. The sun's overwhelming plasma and gravity will make communication impossible. The data from that critical October 3rd flyby must be gathered and sent before this blackout. The Mars fleet is our one chance to get a clean signal before the comet heads to its late October perihelion and disappears into the solar glare. The data blackout is over. As 3 Green Atlas clears the sun's interference in December 2025, it reappears in our telescopes. It is a changed object. Having survived its fiery late October perihelion, it is dimmer, its engine throttling down as it recedes from the heat. Now, the encrypted data packets from the Mars fleet, held since the October 3rd flyby, can be fully downloaded and analyzed. The verdict is in. The science is conclusive. The anomalous brightness was not a single event. It was a cascade, a perfect storm of 3 separate factors. First, the comet was genuinely bright. Its CO2-driven engine was far more active than a typical water-ice comet at that distance, providing a high baseline of gas and dust. Second, the Mars data provided the smoking gun. The MAVEN orbiter did register a sharp spike in solar wind density and magnetic field strength, consistent with a CME glancing blow. Hours later, ground telescopes and the Mars orbiters did register a corresponding flare in the comet's brightness, particularly in the ionized color gas. The sun had, in fact, squeezed the coma, temporarily amplifying its light. Third, This combined real phenomenon was captured by ground-based observers, who then used processing software to stack, stretch, and saturate the images, turning a notable event into the viral spectacle that captured the world. The mystery is solved. The artifact, the solar modulation, and the intrinsic engine have been successfully disentangled, but the meaning is just beginning to unfold. We now have the profile of a visitor from another star. Its high CO2 content and the still baffling nickel-to-iron ratio are not artifacts. They are a message, a fingerprint of the chemical environment where it was born, a system likely very different from our own. As the comet continues its outbound journey, it will receive one last gravitational nudge from our solar system. Its geometry relative to Jupiter on March 16, 2026, will finalize its exit trajectory. JJOBAU-ST may take one last, long look, probing its fading signature. We didn't just debunk a photo, we used our entire solar system as a laboratory. We took a piece of another star's building material, watched it fly past Mars, blasted it with a solar storm, and measured the result. 3i Atlas returns to the interstellar dark, but it leaves behind a data set that will be studied for decades, a true emissary from an unknown home.